Now, regarding buoyant forces and bodies that sink and bodies that float, here is a vessel of water and here's a piece of wood. Floats. Here is another piece of wood. Wood, water. Heavier than water. Lignum vitae. Here is a piece of wood. Heavier than water. So there are woods that sink and woods that float, their densities being less or more than that of water. Now, regarding bodies submerged in liquids, I have here something absolutely enchanting. Here is a vessel of water in which I'm going to put a wooden ball. There. It sinks about, 5/8 or something like that. Now here is a vessel of mercury. Vessel of mercury. I'm going to put the ball in the vessel of mercury. Watch it. It doesn't sink at all, hardly. Hardly. It rides on the very surface. But that's wood. Very light. How about steel? Oh, you know that the specific gravity of steel is about 7 or 8. The specific gravity of water is 1. You know that steel sinks in water. Watch it. Sinks to the bottom. By the way, I say steel sinks in water. On an earlier program on surface tension and the strange behavior of the free surfaces of liquids, I showed in a demonstration where I float a steel needle on water. So steel can be made to float on water. But how about the steel ball in the mercury? Watch it. Oh, this is something. There it is. There it is. The steel floating on the mercury. This is a marvelous thing. Let me use a larger steel sphere, because this is enchanting to see. There it is. Steel floating in mercury. Now, talking about Archimedes leads me to show you a classic mosaic. You remember that Archimedes defended the city of Syracuse when it was attacked by the Romans under the general Marcellus? And then Archimedes was put to death by a Roman soldier who ran upon him while he was doing a demonstration in the sand. So here is that mosaic, which I hope you will see. There is the Roman soldier urging Archimedes, "Come to my general Marcellus." And Archimedes begged him, "Let me finish first my demonstration." And here is another monument to Archimedes, which shows him holding a mirror. This is a little glossy and hard to see. Holding a mirror with which, you remember, he set fire to the enemy ships far from shore. So, what have we discovered here? The remarkable principle of Archimedes that a body submerged in a liquid is buoyed up by a force equal to the weight of the liquid displaced. Now, Archimedes, as you know, apart from being a natural philosopher of the first magnitude, was also a mathematician. And I want to tell you quickly about some things he discovered of a mathematical nature, because they are enchanting. And here they are. Here I have a right circular cylinder, and here I have a right circular cone, and here I have a sphere. They are the same altitude and the same radius. And what did Archimedes discover? He discovered, by playing with these, filling them now in turn with sand, that the volumes were uniquely related in the ratio of 1 to 2 to 3. I'll leave it to you to discover how that ratio goes with respect to the bodies. Now, in his later years, having made many discoveries of great moment and significance, he was asked what he viewed as his greatest. And he referred to this, the ratio of the volumes of the cylinder to the cone to the sphere, and asked that when he dies, such a matter be put atop his tomb, which shows a cylinder, a sphere circumscribed by a cylinder. So here is a sphere about which is circumscribed a cylinder. And this was put on top of Archimedes' tomb, buried near Syracuse. Where are we then in this dialogue? Archimedes, 3rd century B.C., who must certainly rank with Newton of the 17th century and Einstein of the 20th. So next time you go to the sea to bathe, remember Archimedes. And when indeed you take a bath in your bathtub and you submerge yourself in the water and the water rises, remember the affairs here, which revealed that beautiful fact which we use abundantly, because after all, this is why ships can sail on the sea and submarines under the sea and airplanes above the sea. And I thank you for your attention.